Finally, now that we understand what looping variance and loop variance, these two kinds of contract for a loop, really mean for its correctness. So now we would like to see how we can formulate the correctness conditions for any given loop. Again, let's remind us of the syntax. So given some precondition to start with a loop, we have some initialization, we got looping variance, we got exit condition, we got body of the loop, and also we got variance, some integer expression, and also we got a post condition. So now we would like to know what would be the correctness condition that we want to prove in order to conclude that this given loop is formally or provably correct. Of course, if you want to argue that the loop is not correct, you have to give proper counter examples. So these are the summary of all the conditions that you will need to know about, but I'm just going to go over one by one together with you, and then try to show you the step of deriving the formal correctness conditions. Let's go one by one. Let's say we remember the Hoare triple. So we got precondition here, we got post condition over here, and we got the implementation over here being the most complex you can get, which is a loop. Okay, as far as this course is concerned, we don't really consider nested loop, so you don't have to worry. However, inside a particular loop, you may have if statements or assignments, right? Let's now talk about it. So the first one, okay, we want to talk about separation of concern. We talk about partial correctness, and then we talk about termination. So put together, we got total correctness. For partial correctness, we got number one, given precondition Q, the initialization step init establishes Li, the looping variance. So now, how do we formulate this first one here? So you can see this one here. Given precondition Q, initialization simply establishes looping variance I. Right? I'm just gonna stay on this page to show you all the conditions. Okay. Right. For this first one, so given precondition Q, so we just can formulate this as a Hoare triple. Given the precondition Q, the initialization step will be S inits, and then this one here is going to establish the looping variant I. So this will be I over here, right? So this is exactly what you will get over here, right? Let me just make it a little bit smaller. All right, so that's the first condition. What about the second one? It's exactly the same description from the slide, so I don't need to switch back. The second one here, let's read it together. We say at the end of a particular iteration, so by executing the body of the loop, if not yet to exit, which means we are still going to continue, looping variance is actually maintained. So now the precondition here will be a little bit more complicated. So now we want to say this. Basically not yet to exit, and also at the end of certain iteration. We know that at the end of each iteration, the looping variance must be maintained. So we can still have looping variance being part of the precondition, and also not yet to exit. So that means the exit condition here must be not true, so not B. And then by executing the body of the loop for another iteration, we should really maintain the looping variance. So by executing the body of the loop, we are still going to maintain the looping variance. So which means the looping variant will still be the post condition. This one here might require a little bit of thoughts, but I just want to derive together with you quickly. All right, so that's the second one. Of course, it should be just I rather than Li. All right, what about the third one? Let's say this. If we are ready to exit and also the looping variance maintained, the post condition R is really established. So this is the only proof obligation you don't really need a Hoare triple, because over here we don't really talk about any implementation of the code, right? So now, if you're ready to exit, so that means B must be true. And also, looping variant has been maintained from the last iteration, right? So that means Li is also true. That means the R, the post condition, has been established. So that means implies the post condition, right? That's why we say you can think about the looping variance combined with the exit condition. So that justify Li is in some way conceptually is really a specialized form for R, right? You can see Li implies R with the exit condition being true. All right, so this one is also done. Okay, we got two more. So far we are really talking about the partial correctness. You can think about all these three are about partial correctness. Let's talk about let's talk about termination in order to argue for total correctness. The first one, given looping variance and not yet to exit, the body of the loop must maintain the loop variance being non-negative, right? So you pretty much get an idea about how to formulate this using a Hort triple. Let's try it. So given loop invariant I, and also not yet to exit, so which means this must be false. So not B, and then the body of the loop is going to maintain the fact that the loop variance V must be non-negative, which means V must be larger than or equal to 0. So that's exactly what you will get. All right, you can also refer to the better typeset form in the slides. Finally, let's see over here. We say that given loop invariant I and also not yet to exit, which means we're still in the course of decrementing the loop variance V. So it will be strictly decremented. So now we want to be careful here. We want to say between each iterations, we want to make sure the loop variance, the pre-state values is always strictly larger than the post-state value. That's how you formulate decrementing. Let's see this. Let's say here, given loop invariant I, and also not yet to exit, not B. And they want to say the body of the loop is going to decrement the value V. So here we want to refer between V and also V0. You can think about V0 is the LV value. Actually, yeah, because we say V over here, right? So the loop variant value in the beginning of the current iteration. Okay, whereas for the V here is like a post-state value. You can think about it as an LV value at the end of the current iteration. Right? Hopefully you can see that. All right, just let me highlight it. Right? It's either at the end or in the beginning. Right? We're gonna compare them. So now what should be the relationship between them? Well, you want to make sure it's strictly decrementing. So which means this new value must be strictly less than the initial value, right? That's why it's decrementing. So now we're going to say over here, V strictly less than V0. That's what we're going to say. Okay, V strictly less than V0, right? You can see exactly over here, right? So these are the correctness conditions you have to know about the loop correctness. I'm just going over with them quickly just to give you the intuition. Okay, let's go back to the slides. So these are exactly what I just illustrated to you, all right? So now, finally, before I conclude the lecture, I would like to give you one exercise to really complete beyond this lecture in order to really put everything together, right? So this will be the program which we talk about. I want you to apply the correctness conditions that we spoke about, the 5 different correctness conditions for the loop, and you want to prove them all. For the most complicated one would be how to maintain the loop invariance. And for this one here, I already gave you the solution. But everyone else would be quite easy. I shouldn't say easy. It would be quite straightforward to prove if you simply apply what you learned from 1090. Okay, that will be something I would expect you to do. Of course, get to me if you got trouble or difficulties completing the proofs. Okay, so I'm just going to show you one example over here. Okay, how we can formulate the condition. So remember, let's say just for the first one, how do you formulate the proof conditions for initialization? Remember, we said that it's going to be basically given the precondition after the initialization, you should really establish the loop invariance, right? So for this particular exercise, so given the precondition, let's say we simply don't have any precondition for this exercise. We simply assume every time when you're being passed an array, it's just going to be non-empty. We don't even put the precondition down. Let's say we just make it a little bit simpler for this example. So the precondition will just be true. And then this is the part of the initialization you are going to execute. So it's going to be I is assigned to a dot lower sequential composition followed by result is assigned to AI. And what we really want to establish as the post condition is the loop invariance over here. Right? That's the loop invariance. Okay, let me just copy that down just to be complete for this particular example. For every j such that a dot lower less than or equal to j, and also strictly less than I. We spoke about why this should be less than I. And then it is the case that result is larger than or equal to A, J. Okay, you can see it's a very clear Hoare triple. You got precondition, you got postcondition, and also you got the implementation over here, right? That's the Hoare triple that we have been speaking about in this lecture. And that it will be your exercise to really formulate the condition for before termination, upon termination, and also about decreasing variance and also non-negative variance. Okay, so these are all the 5 conditions that we spoke about over here. So you really want to do this by yourself before you look at the solution. Otherwise, you might just get trouble understanding what's going on, when you are in a test. So I would highly encourage you to really do that before you look at the solution. So if you go back to the slides, let me just finish the lecture here. So you can see, so these are basically the solution. I would suggest don't really look at the solution until you're done with the exercise. Okay. And so here are just 2 proof tips for you, okay, before I assign to you the exercise. So whenever, let's say this, whenever you actually are given, let's say this particular Hoare triple to prove, and the precondition is simply Q and P. Sometimes you might find that the P over here may not be so useful in order for your proof to proceed. So you can simply just discard it. So which means in order to prove this particular Hoare triple, it would be sufficient if you simply prove this particular Hoare triple by getting rid of some precondition over here. That's actually fine. Okay. So now this is the basically the proof rule. You might find it useful later when you do the exercise. And this will be just the proof of this particular rule. And the idea will be we simply just formulate the Q and R. And then you will know that in order for this to be a tautology, so this will be the implication. And also we also formulate the proof conditions for this one here using implication, and then you can see easily how these two are actually this one will actually imply this one over here, right? Okay, for the proof, I'm just going to let you go over. It's actually quite clear and straightforward. I'm not going to waste your time over here. But you can definitely simply apply this particular rule whenever you find applicable, all right? Again, you can, whenever you're given particular precondition with conjunction, you can feel free to get rid of any one of them and simply try to prove this one instead. It's going to be acceptable. Okay, proof tip number 2. Basically, whenever you are going to calculate the weakest precondition, and if the desired postcondition involves certain indexing notation, you really want to also augment the particular postcondition over here by the fact that I should be also a valid index. So which means you should really say this. So what you really want to establish upon the termination of S will be not only that AI should be larger than 0, but it should be also a valid index. So this will be also important for you to augment. Okay, that's another proof tip that you want to consider when you actually do your exercise. Okay, so that's about the 2 proof tips. And then finally, you want to go into this particular PDF. You can go to the link. Let me just show to you very quickly about what that particular exercise is about. We basically already went through with you. Okay, let's now quickly. All right, so this is the exercise. That's the program, basically the same as what we discussed in the lecture. And now, so here are the various questions you might be asked later. So I just want to get you prepared, well prepared for whatever test or exam you might have later. Okay, so you want to stay formally all the 5 conditions. You can also see the solution either in the next page or you can see that in the slides. Okay, and also for each one of them, you want to first of all calculate the WP in order to prove that the Hoare triple is actually tautology. Step number 1 will be to calculate the WP, and step number 2 will be to argue that whether your existing precondition is actually stronger than the calculated weakest precondition in the first step, right? That's something we also spoke about. We actually did a swap program in the sequential composition part of this lecture, and then you should know the 2 steps already. Okay, so now you will see the again the solution for every one of them. You can see that here is the augmented postcondition, precondition, postcondition to be proved, right? Because you're doing indexing over here, you want to make sure this index over here is also valid. Okay, that's something you want to remember. Okay, and this part here is really the solution for the proof obligation number 2. Okay, about let me show it to you. about maintaining the looping variance. So I would suggest give a try on this before you look at the solution. The solution itself, it's actually in structure not too complicated, but you do have to try it yourself before you look at the solution. All right, so that's about the final topic of this course about program verification. So it's been a long semester about covering the various topics about software design. I would like to finally just remind you about this diagram which we learned, which we saw together in the very first part of the semester. Remember this diagram over here? So now you can, maybe this diagram here will be a very useful tool for you to reflect on what topics you have you actually have learned in this course. So I hope I cover almost every topic over here in depth and also in details, and also we got a Q&A to help you. And then there will be another Q&A for this particular last lecture for program verification. I will also try to schedule maybe 2 to 3 exam review session to really help you to get you prepared for the exam. But beyond this course, I really hope that any knowledge you learn about software design, hopefully you'll be transferable, not just restricted to IFO, but it will be transferable to your particular programming language you're going to use. Okay. All right. Anyway, so it's been a very pleasure to really have the journey together with you. So wish you all the best, and then have this diagram here to think about what you really have learned, the work you have done, and then and then I'll see you in a future Q&A session or the exam review session.